Now let's start section 2.3, power factor. Based on the previous analysis, we know that um, we can draw three conclusions. The first one is that the current flowing through any of this component, such as resistors, inductance, and capacitors, will have the same frequency as the source of the voltage. The second conclusion is that there can be phase shift between current and the voltages, depending on the combination of resistors, inductance, and capacitance. And finally, the last conclusion is that resistive elements are the only component that dissipated any net energy, because the average power of capacitors and inductance are zero. So the resistive elements are the only elements that dissipated the power. So imagine that there is a black box containing any number of ideal resistors, capacitors, and inductors. Now, they can be wired in any way. The voltage source in this box has a RMS voltage V, and we can assign the voltage, this angle, the voltage source, the phase angle theta as 0. Now, since the current delivered to the black box will have the same frequency as the voltage source, therefore we can write as I equal to square root I multiply cosine omega plus theta. The instantaneous power supplied by the voltage source and dissipated by the circuit in the box is written as P is equal to V multiply I is equal to the square root V multiply cosine omega t plus square root 2 I cosine omega t plus theta. Then we apply the trigonometric identity. We can obtain the P is equal to Vi cosine omega t plus theta plus Vi cosine minus theta. Since the average value of the first item, Vi cosine omega t plus theta is equal to 0, therefore, and the cosine x is equal to cosine minus x. So the P average is equal to Vi multiply cosine phi, cosine theta. And this cosine theta we define as the power factor. So the power factor is the average power dissipated in the box is the product of the RMS value voltage supplied times the RMS current delivered, and then times the cosine angle between the voltage and current. So the power factor is the cosine value of the angle between the voltage and the current. So the power factor PF is equal to cosine theta. Most of utility customers pay only for the watts, which is the real power used by them. The utility has to cover the losses, the I square R, the transmission line losses and distribution line losses. And if a customer has a voltage and current way out of the phase, which means the power factor, we call this power factor, is very poor. Therefore, the utility has to pay or cover more losses on the transmission and distribution lines. So usually, utility will ask customer to maintain a good power factor, which is PF is equal to 1.0, which means the cosine theta is equal to 0, and the theta is 0, which means that the voltage and current will be in the same phase. So the load of the customer, the ideal load of the customer should be resistive load. Now section 2.4, the power triangle and the power factor correction. Now let's look at this graph. We want to find out the power triangle. Since the P average is equal to V multiply I multiply cosine theta, is a VI multiply power factor. This line is called the apparent power, and it's equal to the real power, which is P is equal to VI cosine theta. The reactive power, Q, is VI cosine theta. So that is called the power triangle. And the real power is actually the real work. So, and the reactive power is when to be able to deliver the real work, the real power, they have to generate the magnetic field and then to be able to enable the power to transfer through those transmission lines. And utilities are very concerned about the customers who draw a lot of reactive power, because reactive power increases line losses for the utility, but does not result in any real work, does not result in any more kilowatt hours of energy which we sell to the customers. So that means the utility will not be able to receive revenue by generating or by delivering reactive power. So utility will charge a penalty if a customer will have a poor power factors, which means that the utility will ask those customers who has poor power quality will not only to pay for the kilowatt hour, which is the real energy used, but also has to be able to pay the reactive power, the kilowatt hours used by the customers. And most of the large customers, their load are electrical motors. So their load are inductive load. So how can the power factor be brought closer to a perfect 1.0? As we know that most of the customers who have the inductive load, because they use the electric motors, and therefore in order to bring the power factors to 1.0, we usually add capacitors to offset that. The capacitor provides the current that the inductance need, and the capacitor also get current from the inductance. So the current will oscillate back and forth between the inductance and the capacitors. So this graph shows how we're going to compensate for the reactive power or correct power factor. This left side graph shows the normal condition. Most of the load is an inductive load with some resistance. And in order to correct the power factor, we usually add a capacitor in parallel with the inductance. So this will help to reduce the phase angle between the voltage and the current, and then have the more power be utilized by the resistive load. And this shows the relationship between the current through a capacitor. The V is equal to 1 divided by omega C multiply I. So the VAR provided by the reactor is that equal to V multiply I is equal to omega C V square. So this means that the rating of a capacitor depending on the square of the voltage. So if we know how much reactive power that is needed by a customer, we can use this equation C is equal to VARs divided by omega V square to determine how much capacitor we need to add in parallel with the load for the power factor correction. So that will help us to determine the capacity of the capacitor. Now let's finish the section 2.4.